Hey there, everybody. Welcome back. Let's look at conservative vector fields and the curl of the gradient. So let's say we've got some scalar function phi has continuous second order partial derivatives. Then the curl of the gradient, we're using the del operator, del curl del phi, or the gradient of phi, is 0. And if we say f is that the gradient of that scalar field, our vector field f is the gradient of the scalar field f, then we've got the curl of f is 0. So we can work out a little math and show it. If we do ijk on it, do the curl, you see the I component we've got, and I use the subscript everyone likes that doesn't have the d squared over dz dy. So this is the partial derivative with respect to z, then y, minus the partial derivative of phi with y, with then z. Then we've got j, it's got z and z first, then x, minus x first, then z. And on k, we've got y first, then x, minus x first, then y. I'm being lazy and saying partial derivatives there, but each of those balances out to 0. So we've got a 0 vector field. And that, remember Clairaut, we talked about that. When the second order partial derivatives, they're the same. So if we've got some vector field f and it's the gradient of some scalar field, it's called a conservative field if the curl equals 0. Curl equaling to 0 means it's not rotating there. It's irrotational is how the terminology for it. And the fact that curl of any conservative vector field is 0 gives us an easy way to verify if a field is conservative. We will like conservative fields later on, you'll see it. So an example, we had the curl of f was, f was xz, xyz, and then negative y squared. If we do the curl of f, as we did before, we had it equaling to negative 2y minus xy, then x, and then xz. This is clearly not 0 unless x, y, and z is 0, but that's only a single point. So f is not a conservative vector field. When we do the curl of a vector field at a point, like in this last one, 0, at 0, it means there's no rotation. X, y, and z would be 0, so the curl is 0 there, but everywhere else around it is swirling. So it's like stagnant at the origin, but everywhere else the water is swirling around it. So whirlpools, eddies, stuff like that, you get some turbulence. That's it for this video. We'll do some examples with conservative vector fields in the next one. Peace.